All right, guys, so let's take a moment, if we could, and do a bit of summary and comparison between the three major ideas that we have looked at thus far in this unit. The three major ideas that we have looked at are cell potential, voltage, Gibbs free energy from the thermodynamics unit, and now the equilibrium constant, K. So I like to call it EKG. Because the cell potential is E, Gibbs free energy is obviously delta G, and then the equilibrium constant is K. So I call it EKG. What we learned throughout each of these aspects is that there's a different set of rules for each of these guys as far as what we are looking for with their particular aspects. Now, I have summarized these rules down here at the bottom of this sheet as far as the math is concerned. But let's go ahead and add in a factor here for factors that are thermodynamically favorable, which is a big old fancy way of saying that the reaction actually goes, right? So what are we looking for E? What are we looking for K? And what are we looking at for delta G for the reaction to actually go? So if it's going to be thermodynamically favorable, then what we need is a voltage that is greater than 0 or a positive value. So just a reminder that batteries actually go when they have positive voltages, right? What do we know about product-favored reactions for K? Well, we know that they are greater than 1, because remember that K is the products over the reactants. And if we want the reaction to go to the right, which we usually do, then we are going to want a lot of products and very few reactants, because again, it's reactants to products. We want it to go over to the right. We want big products and small reactants here. Big and small there. And so we want the K value to be greater than 1, all right? And then for delta G, if we look at it from a thermodynamics perspective, we want actually delta G to be a negative number here, if we remember that. So just a quick reminder that there are three kind of different games that we are playing here. Voltage, equilibrium constant, and Gibbs free energy, and they are all similar to each other, but they all play by different rules. Another quick reminder here that each of these guys has a different way of dealing with each of the Hess's law / stoichiometric changing the factors of each of the processes. So for example, remember that if you reverse an equation for voltage, what you're going to do is you're going to take the opposite sign of it. For Gibbs free energy, you're going to take the opposite sign of it. So if you flip an equation, you just take the negative. But remember, for K, that's a little different. For K, you're not going to take the negative of it, you're going to take the inverse of it. It gets even weirder when you start to talk about things like changing the stoichiometry. In changing the stoichiometry, if you double an equation for the voltage, it has no effect, right? If you double the equation for a K value, you actually square the number. You don't multiply it by 2, you square it. And it only when you get over here to delta G that if you double an equation, for example, then you're going to multiply that delta G by 2 over here. And then what happens when you add equations together? Well, if I add equations together for voltage, I just add up their voltages. It's easy. I do the same thing for delta G over here. But for equilibrium, if I add up equations, I don't add the K values together, I multiply the K values together. So this chart here is just kind of a summary of all the weird and wacky little different things, intricacies that you need to have memorized when you go into the AP test. So this is an important one here for you to remember. And again, remember which ones are thermodynamically favorable. And obviously, if I were to change the question to thermodynamically unfavorable, it would be the opposite of each of these guys, right? It would be a negative voltage instead of a positive one. It would be a positive delta G instead of a negative one. And it would be a K value that is less than 1 instead of one that is greater than 1, all right? So we're playing by three different sets of rules here, but that doesn't mean actually that we can't convert back and forth between them. There are a couple of equations, both of which are on the equation sheet that you're going to get. So you don't have to memorize these, which is great. You just have to know how to use them. And the two equations are as follows, that if you want to transfer back and forth between delta G and E, you're going to use this equation here, where delta G is equal to negative NFE. We have seen actually all of these things before. Let's take a quick moment to remind ourselves what these things are here. So delta G is obviously the Gibbs free energy. E is obviously the voltage. Right? It's obviously the voltage that's there. And the only two that you might not remember because it's been a while are N and F. Well, F is just Faraday's constant, 96,485 joules per volt mole. Again, you don't have to memorize that. It's on the equation sheet. And N is the number of electrons being transferred in the overall reaction. I'll give you an example of that in a little bit. So F is just Faraday's constant, 96,485, and remember it's in joules. That'll be important later. And N is just the number of moles of electrons. All right, now if you want to go between E and K, then you're going to use this equation here, where the log of K is equal to NE over 0.0592. Again, it is on the equation sheet. You do not have to memorize it. Where does this equation come from and how do we use it? Just like the other one, who cares? It's just an equation. We're not going to get into the specifics of why it is. I could justify it, but it would be a long and boring lecture. And if they were to ask you this question, there's no guarantee that they are. Really, you don't have to justify anything except by plugging the numbers in. So if you'd prefer, you can write it like this, where it's natural log of K is equal to, N E over 0.0592, right? Same thing. It's the same. It just looks a little bit different, right? So, but again, these equations are on your equation sheet there. So, again, K here is just your equilibrium constant. And then E is your voltage. And again, N is the number of moles of electrons. All right. So let's get into an example of it. So here's example one. It says, using the following reduction potentials, you're going to want to create a battery and you're going to want to calculate E, K, and G for each of these guys. All right. So first of all, please note that both of these reactions are written as reduction, as you would see on the reduction potential chart, right? Both of the electrons are on the left-hand side. So if I want to create a battery for this, then what I'm going to have to do is I'm going to have to flip one of them. Remember that I'm always going to flip the one that is less positive. So that means I'm going to have to flipify this one. So I'm going to have to go with 2 Br negative is going to flip over here to Br2 plus 2 electrons. And in flipping it, my voltage becomes negative 1.09 volts, right? As per our discussion of these guys down here. Remember, if you reverse an E, it goes to the opposite sign. Yes, you got to begin to keep all that straight. And now, if we take a look at this, we've got 6 moles of electrons being transferred here and only 2 moles of electrons being transferred here. So we're going to have to multiply this whole bottom equation here by 3. So then we end up with 6 of those and 3 of those. And now I'm going to have 6 electrons here. Now remember that in voltage, when you multiply an equation by 3, what happens to the voltage over here? Nothing, right? Because it's an intensive property. And again, that goes to this guy over here. What happens if you change the stoichiometry for a voltage equation? It's no effect. So in this case, we tripled it, right, instead of doubled it. It doesn't matter. There's no effect. If this were K, right, then we would be taking it to the third power. And if this were delta G, then we would simply be multiplying it by 3. But in this particular case, nothing happens, right, because it's voltage. So now we've got everything that we need. We've got our Cr2O7, we've got our 14H positives, we got our 6 Br negatives, we got our 2 chromium plus 3s, our 7 waters, and our 3 bromines here, and our 6 electrons cancel on both sides. So what is going to happen here? Well, the first one is the easy one. We can figure out what the voltage is. If I want to figure out what the voltage is between these two things, I just have to add them up. So this is 1.23 added up with a negative 1.09. I get a voltage of positive 0.14 volts, which makes a spontaneous, thermodynamically favorable reaction because the voltage is positive. Now, because I know that E is positive 0.14 volts, I can calculate delta G and I can calculate K. All I have to do is plug things into that equation. So delta G is going to be equal to negative NFE. So delta G is going to be equal to negative, well, the E is easy, that's positive 0.14. The F is easy, that's 96,485 joules per volt mole. And again, that's volts, so my volts cancel. The only question is in the moles of electrons. Well, once we balanced this bad boy, it was pretty obvious that we had 6 moles of electrons being reduced and 6 moles of electrons here being oxidized. And so consequently, our number of moles of electrons is 6. It's not 12. Because remember, the same electrons here that are being oxidized, 6, is the same, they're literally the same moles of electrons. They're being lost here and they're being gained here because they are going from this side over here to this side over here. So again, it's not, you don't add them together, 6 plus 6 to 12. They're literally the same electrons. So you just got to make sure that we've got 6 moles of electrons here. So now my moles cancel and we're left with joules. So we have 0.14 at 96,485 at 6. So I get a delta G then of negative 81,047 joules. And usually they'll want you to change that into kilojoules. So you're really probably looking at a better score of negative 81.0 kilojoules that's there. Okay. So that is our delta G that is there. Using our very simple equation, delta G is equal to negative NFE. All right. Now, what about the other one? What if I wanted to get K? Well, I'm going to use this new equation here. The log of K is equal to 0.0, or N times E divided by 0.0592. So the log of K is going to be equal to those 6 moles of electrons times my voltage, which is positive 0.14 divided by 0.0592. So that's going to be 6 times 0.14 divided by 0.0592. So that's going to be the log of K is equal to 14.19. And if you remember from your math classes, how do you undo a log? You take the 10 to the function. So you're going to take 10 to the log of K, and the 10 to the log cancel each other out. And so you end up with K is going to be equal to 10 to the 14.19. So 10 to the answer there gets me 1.54, 1.55 maybe, times 10 to the positive 14th is equal to your K value right there. So armed with a voltage, you can calculate the delta G and you can calculate the K by using our 2 new equations that I gave you here, which are this guy here and this guy here. All right. So as long as you have the voltage, you can get both of these guys. One more, and then we'll be done. It says make a battery using the following shorthand notation. So it looks like we're going to be oxidizing iodine and reducing the iron plus 3 to the iron plus 2. That's there. So we have these 2 guys here. Please note that they are both written as reduction, as one would expect. So we are going to have to do 2 things. We're going to have to flipify one of them. You always flipify the one that is the less positive, the more negative. So we're going to flip that guy, and we're going to go 2I negative is going to come over here to form I2 plus 2 electrons. As soon as I flip that, that becomes a negative 0.53 volts. And now I've got 2 moles of electrons being transferred here and only 1 mole of electrons being transferred there. So I'm going to have to double this whole thing here, 2, 2, and 2. What does that do to my voltage here? Nothing, because again, when you change the stoichiometry in electrochemistry, nothing changes. So that is our overall equation. I simply add these guys together, and that looks like it's going to be what? Positive 24 with math in my head. Let's make sure that we're right here. Yep, positive 24 volts that's there. So knowing that my E is positive 24 volts, can I calculate delta G and K? Let's see, delta G is equal to negative NFE, so delta G is going to be equal to negative 96,485 times 0.24. Now, how many moles of electrons are being transferred? Well, remember, we had 1 and 2, so that's why we had to double this whole equation. So it's really 2 moles and 2 moles here, so it's 2. So I've got 0.24 at 96,485 at twice is going to get me a delta G of negative 46,313 joules, or a delta G of negative 46.3 kilojoules, which makes sense because it's thermodynamically favorable because of that negative delta G that's there, and because I have a positive E. Positive E's are batteries. They are spontaneous. They are thermodynamically favorable. They just go. So if you were to hook this guy up, he would just go. And then finally, our other one here is the log of K is equal to nope, I always want to put that on top. NE over 0.0592. So the log of K is going to be equal to 2 times 0.24 divided by 0.0592. So the log of K is going to be equal to 2 times 0.24. 0.0592, 8.11, or K is going to be equal to 10 to the 8.11. So that's that. Looks like it's about 1.28 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, according to my calculator.